Okay. So, thank you. It's a pleasure for me today to present the topic of string attractors. And maybe to just briefly introduce myself at the beginning. So I'm a master's student at the Czech Technical University, although currently I'm studying this year here in France as an Erasmus student. And so I will be presenting the topic of string attractors of Rote sequences, which is a joint work with my supervisor Luca Dvořáková. My presentation will consist of 5 parts. Well, first I will say a few words about the motivation behind string attractors. Then I will introduce the string attractors themselves, and I will give some overview about them in the context of combinatorics and words. And the main part of my presentation will be talking about closures. First, I will be speaking about palindromic closures as a way to generate Sturmian sequences. And then I will generalize this idea for generating generalized pseudo-standard words, and especially the Rote words or Rote sequences. And in the end, I will present a few open questions that we have and that arise from our research. So I will start with the motivation, although I believe that everyone in this room is already motivated enough, but I will still say it. What drives the interest in string attractors is their potential to unify the repetitiveness measures that we obtain from dictionary compressors. And well, compression is a very broad field nowadays, and we have different types of compressors for different types of data. And when we look at highly repetitive data, for example, the genomic databases in bioinformatics, which grow very, very quickly now, then they have dedicated a special class of compressors, which are called the dictionary compressors. Here I have 3 examples, although there are more of them. You can see the Lemplziv methods, the pointer macro scheme, or grammars, or so-called straight-line programs. And using these compressors, we obtain something that's called repetitiveness measures, which is the measures of the repetitiveness of the input that we put into them. And so it's usually the size of the data structure. For the Lemplziv methods, it's the size of the parsing. For the pointer macro scheme, it's the size of the scheme. And again, here for grammars, it's the size of the straight-line program. And so here we have 3 different compressors, or even more, and we get 3 different measures. Well, the measures probably will give us different numbers. And so this is where the string attractors come to play, because using them, we can we can express the spaces in which these measures will fall, as I would say. And so here on the right, I put stars to the letters. That means I'm talking about the smallest possible size. And the gamma with the star means the size of the smallest string attractor. So these are just examples of the expressions for these measures. And they were originally presented by Veronika Hendrychová in 2018. And so it also goes a little bit the other way around, because from the dictionary compressors, we also get upper bounds for the attractors. They give us hints on where the attractors are, but they are not always minimal. So it's kind of upper bound. And from this, we can say that dictionary compressors can be interpreted as approximation algorithms for the smallest string attractor. So an advantage of this is, of course, that the string attractors are not dependent on any compression method. So it's defined just on the word without anything else. But the disadvantage is that in full generality, it's NP hard to obtain the minimal string attractor. And this is where the combinatorics on word approach helps us, because we can look at a little bit constrained pool. We can take, for example, special classes of words which obey some rules, and we can address this a little bit easier problem much more effectively. So this is what I will be talking about, and now let's look at what string attractors are, the definition, and what we already know. I will be talking a lot I'll be talking about occurrences. So here's just a definition of occurrence. If I have a finite word and I have a factor in it, let's say from the position I to j, then occurrence for me are all the positions from I to j. And of course, factor can have multiple occurrences in one word. And so here's the definition of string attractor. So for a finite word w over some alphabet, the string attractor is a set of positions. Here I will denote it by gamma, such that every substring I take in the string, it has an occurrence that contains some element from gamma. So let's look at an example. It will be maybe easier to grasp this. So let's say I have this word w that you see, and I would like to persuade you that this gamma, the positions 2, 3, 4, 8, and 10, are a string attractor of this word w. Here on the right, you see the positions in green. And so what do I need in order for the gamma to be string attractor? Well, any factor I take in this word, it must have an occurrence in the word such that it contains some green position. So for example, this factor is 0, 1. It's not green on the beginning, so I have to find it somewhere else in the word. So we see that it's in the end, and it contains a green position. So if I do this for all factors, then I can say that gamma is a string attractor. It's not a unique set. We can also throw out the position 8 and still this will be a string attractor, or we can have a completely different one. So it's not unique, but what is unique is the size of the minimal one. So the minimal size is what's interesting for us. And so string attractors have been studied in combinatorics on words for some time. And I will be talking a lot about sequences, which are usually, I mean by this, an infinite word. However, the definition of string attractor is for finite words. So usually the way it is studied is that for the infinite sequence, we take some factors for which we study it. For example, for the particle prefixes, and for that it has been determined for the standard Sturmian sequences by Mantaci, Restivo, Romena, Rossone, and Scortino. I hope I'm pronouncing it right. And also for the tumor sequence, it was by Kutsukake in 2020. Also for prefixes in general. So for that we know that for the standard Sturmian sequences, for the Fibonacci sequence and tumor sequence, and the period doubling sequence and powers of 2 sequence, all by Scheffer and Charlotte in 2021. And also in general for factors of sequences, like for the episturmian sequences by Veronika Hendrychová, and for the tumor sequence by Francesco Dolce. And also there are other works connected to string attractors, for example, the study of them in linearly recurrent and automatic sequences, and also the combinatorial properties of string attractors have been studied, and them in fixed points of morphisms. Then again as a combinatorial object from data compression, and they've been also studied in fixed points of Fibonacci-like morphisms. So this is probably not exhaustive overview of them. Now we will move to the closures, which will be the main part. So I will drink. So I believe everyone knows what a palindrome is. So I will be working with palindromes, which are words that I can read backwards and forwards, backward and forward, and I get the same word. And a palindromic closure is an operation on a string such that when I'm given a word, then palindromic closure of the word is the smallest palindrome that has the word as a prefix. So I'm completing the word such that it's the smallest possible palindrome. And using this, how to generate the Sturmian sequences, I can take any binary sequence, so I can choose whatever I want, any binary sequence, which I will call the directive sequence. And I will be taking letters one by one from the sequence and adding it to my generated word. And after each addition, I will make a palindromic closure. So I will again show an example how does it work. So let's say I want to generate the Fibonacci sequence. So for that, I will take directive sequence of zeros and ones repeating. And so how does it work? I will first take one letter from the directive sequence, which is my prefix 1, and I will make a palindromic closure. Well, here it's already palindrome, so nothing happens. So the next step is to take the next letter, which is 1, and now I will make palindromic closure. So for this word, it's 0, 1, 0. And again, I will take another letter, and I will make a palindromic closure of this, so I get my third prefix. And by repeating this by taking letters from the directive sequence, I will be obtaining longer and longer prefixes of the Fibonacci sequence. And so when you look at the highlighted positions, which I left there from the letters I was taking, they mark the longest palindromic prefixes followed by the distinct letters. In this case, followed by 0 and followed by 1. So what I mean by this, for example, here in U5, this part from the beginning to the yellow one is the longest palindromic prefix followed by 1 in the word. And so how do we find attractors from this? Very straightforwardly, the longest palindromic prefixes followed by distinct letters mark attractors for all palindromic prefixes of the standard Sturmian words. And what is nice is that it works also for bigger alphabets. If I don't constrain myself only to binary alphabet, but I take any alphabet I want, it works the same. So let's look at the Fibonacci sequence, and you will see basically the same what I did for the Sturmian sequence. Here, that's another letter, so I make palindromic closure, so this is again a palindrome, and I continue the same way. And again, the highlighted positions in the prefixes, they form the attractors for the prefixes of these sequences that are generated by palindromic closures, and they are called episturmian sequences. So they're kind of generalization of the Sturmian words. Okay, so this was the part with the palindromic closures, but we can also have other type of closures. And first I will talk about the Rote sequences, and then we will see how they are connected. Well, Rote sequences is a class of words that are connected to Sturmian sequences in a quite natural way. But the general definition is that they are binary sequences that have complexity 2n, and they are such that their language is closed under letter exchange, sorry. And so how are they connected to Sturmian words? We will use something that we call word sum, and basically means that we take the binary word, and we take adjacent letters, one pair by one, and we make a sum modulo 2. So here it's better seen on an example. We have the word W, and the sum of this word is just sum of 2 zeros, which is a 0, and sum of 0, 1, which is 1, and then sum of 2 ones, and it's 0, because it's modulo 2. And so the connection between them and the Sturmian sequences is that a binary sequence is a complementary symmetric Rote sequence if and only if the sequence, the sum of the word is Sturmian. So we have this connection, and now it's natural to ask, how can we obtain the attractors of Rote sequences from the Sturmian sequences? Because we know attractors for Sturmian sequences. Well, the answer is a little bit disappointing. It seems that we cannot. It seems that at least with the attractors that we know now of the Sturmian words, we cannot do this. Here is just a little counterexample. When I take this word as a Rote word, then in this case the factor 1, 0 is unique in the word. And so in order to find an attractor of this word, I have to have one of these positions in my attractor set, because I need to capture this factor. And if I make the sum of this word, I get this Sturmian word, and the corresponding position is this one. So the attractor should contain this position if I want to look at it, that the attractor is in the same place. However, the currently known attractors of Sturmian words look like this. So here on the left you can see the ones with palindromic prefixes. Here on the right you see those that were known before. And there is no straightforward way, at least we don't see it, how we could obtain this position from these two. So it doesn't work so simply, but it's not the end of my presentation. We can generate the Rote words also in a different way, and using something that's called pseudo-palindromic closures. So I was talking about palindromes. I will be talking also about antipalindromes, only on binary alphabet. So antipalindrome is something that I read forward and backward the same, only with the difference that when reading the other direction, I will get exchange letters, 0 for 1 and 1 for 0. And antipalindromic closure works the same. So as a palindromic closure, only with the difference that I'm completing the words so that I get the smallest possible antipalindrome of the word. And so we can have an algorithm for generating so-called generalized pseudo-standard sequences. And that means that I will be using both palindromic and antipalindromic closures in a way that I will be given in my directive B sequence. So I will be given a sequence of zeros and ones, or just binary sequence, and I will be given also a sequence of closures. So something that tells me when to use the palindromic and when to use the antipalindromic closure. And then it works the same as before, so I will be taking the letters and making the closures after each step. And so this will generate the generalized pseudo-standard sequences. And there is a theorem by Blondin-Massé and others from 2013, which specify that the Rote sequences are actually a subset of these generalized pseudo-standard sequences, which I can get by this algorithm. And so it tells us that as long as we avoid these patterns in our B sequence, then we will be getting Rote words by this algorithm. So it only tells us not to take, for example, 2 antipalindromic closures in a row, and not to take 2 same letters when we are doing 2 palindromic closures, and also the third one. So we can get the Rote words using the closures. Now let's look at how it works. So I'm avoiding these bad factors in my B sequence. So I will take, for example, this one. So my letters will be 0, 0, 1, 1, 0, 0, and the closures will be palindromic, palindromic, antipalindromic, and so on. So the first I take the 0 and make palindromic closures. I end up with 0. Then I take the 0 again and make palindromic closure. Well, nothing changes because it's palindrome. And now I take the 1 and I make antipalindromic closure. So I get antipalindrome. That's the W3. And then I continue with the 2 B sequences, with the B sequence. And so here what I'm getting are longer and longer prefixes of the Rote sequence. And so now another question is if we can use the longest pseudo-palindromic prefixes followed by distinct letters to obtain attractors of these sequences. I think that I haven't mentioned that what I mean by pseudo-palindromic. I mean, when I say pseudo-palindromic, I mean either palindromic or antipalindromic, so I don't have to make the distinction. And so how can we use it? Or the answer to this question is yes. Now let's look at how. So here's the main part of my presentation. So this is a theorem that, yes, you can look at this. So we have formulated this in a theorem with Lubomíra Dvořáková, and here it is a little bit simplified, but you can find the full version in our paper. And I think this is a good time to say that our paper, we have submitted it for discrete mathematics and theoretical computer science. And just a few days ago, we got the review results, and it seems that it will be published with minor changes. So that's for the news, and now look at the term. So let's assume that I have the directive B sequence of a standard complementary Rote sequence, and it's a full word. So let's say it contains both letters. And so this time we are not only looking at the closure that we made, but we are also looking at the previous closure. So if the prefix currently is antipalindromic, then the word has this attractor, where the WI means the longest antipalindromic prefix, followed by the other letter then which was used for generating this one. If I have a palindromic prefix and the previous was antipalindromic, then the attractor has this form. So we are looking at the longest palindromic prefix followed by the other letter then which was used to generate this one. And the last case, when I get a palindromic prefix and the previous was also palindromic, then now it's easy, then the attractor doesn't change. It's the same for both of the prefixes. And so you see that it's a little bit more complicated than for the Sturmian words or epistemian words, for example. And it's also because it depends not only on the current closure that I use, but also on the previous one. So when we look at how it works for the example that you have already seen, then here I have generated these prefixes, and now my theorem tells me the form of the attractors for the prefixes which already have both letters. So here in this case, this word is antipalindrome, and the previous one was palindrome. So I take as attractor the position of the longest antipalindromic prefix followed by 0 because this one was 1, and the length of the previous word. So this is the position 0, and the position 1 here. And maybe I should mention why this is the 0, 1, the 0 here. Why is it the longest antipalindromic prefix followed by 1? Followed by 0. Well, here in this word you don't see, the only antipalindrome that you see is the prefix whole itself. There is no antipalindromic prefix which is not the whole W3. So that's basically the empty word, and the empty word followed by 0 is here on the beginning. So that's the reason why there's the position. When we look at the next one, then the theorem tells us that it will be the length of the longest palindromic prefix followed by 0, and again the length of the previous word. So here the longest palindromic prefix followed by 0 is this 0, and the length of the previous word was this. And in this way, we are obtaining the form of attractors for these prefixes. And yes, here we get the case where we have two palindromic closures in a row, so the attractor doesn't change. Okay, so now I see I'm a bit ahead of time, but it will be more time for questions. I'm getting to the open questions that we got from what we were looking at. And that's the question, for example, what are the attractors of prefixes of generalized pseudo-standard sequences? That means that these are the sequences which we get from using palindromic and antipalindromic closures, and we do not avoid anything. We can take just arbitrary B sequence and arbitrary sequence of the closures, and we are asking about attractors for these, because currently what we showed for the Rote sequences is that the size of the attractors is 2, the minimal size, and also a word that comes to this family of words, the generalized pseudo-standard sequences, is the 2-more sequence, and for that we know that the minimal size of the prefixes is 4, and also we know that for pseudo-standards, for the pseudo-standard sequences, the minimal size is 3. Well, this sequence is are generated such that we only use the anti-palindromic closures. So we're not making palindromes at all. We only take a sequence and we are making anti-palindromic closures one by one. But generally, if we take any sequence of palindromic and anti-palindromic closures, we don't know in general. Also, another question could be what about the attractors of the pseudo-standard or generalized pseudo-standard sequences over larger alphabets, because we can define anti-palindromes also on larger alphabet than just binary ones. So the question could be how it works in this case. And now for the end, a question that's connected more to the beginning, to the motivation of string attractors. If we put the words for which we know the attractors again into the dictionary compressors, the question could be, how do they behave with them? If we have a constant size of the attractor for longer and longer prefixes, does that mean that the compression methods will produce a constant size of the output? Well, or how does it behave? So that are the questions, and yes, I will thank you for your attention.
Questions? Oh.
So you first tried to get the result by studying the Sturmian words and then working the way back to Rote words, but then you needed to do another approach. But can you now, from these results for Rote sequences, easily derive the result for Sturmian words?
Yes, that's a good question. I was looking at that, and it's I found a counter example that tells me that it's not possible. That when I, at least with this form of the Rote attractors that I got, and I put it back to the Sturmian words in the natural way by the sum, and I didn't get an attractor.
Okay, that's interesting. So it's like a similar result for both, but they don't work well together somehow.
Yes.
Okay.
Hi, thanks for the talk. I was wondering if you had any results on factors of such words. So in this case, if I get it right, you covered mostly prefixes, but for instance in the work on episturmians. So I wonder if you had any results on factors of these words instead of just prefixes.
Yeah, it's like the natural direction of the research, but for now, at least I don't know about any results for the factors. I haven't looked at it yet.
Okay, thanks.
Okay, a more general question. Maybe you know something. Are there any more general results, for example, for some specific class of morphisms? Can you prove that, say, for all prefixes, attractors are bounded, size of attractors are bounded? Say for uniform or some even easier subclasses of uniform morphisms. Are there are you aware of any more general results of this sort?
Yes, I understand the question. I think that maybe you know better than I do, but maybe some of the answers for this could be, if I get to the beginning, could be in the work here, which here the fixed point of morphisms has been studied, but to be honest, like from my head, I am not able to say about any results because I was focused mainly on studying the Rote words and the closures and so on. So I don't know from now.
There is an upper bound that at least is constant, is increased when the morphism is applied.
Okay, thank you.
Yes. Thank you for the answer.
Yeah, maybe you can repeat the
Sorry, no, I was saying that for in this case it is known, for instance, that when some morphic words, for instance, generated by morphisms, they basically have a constant increase in the Lempel-Ziv, for instance, and this is a natural upper bound for the size of a string attractor. So at most, this increase could depend on the size of, on the structure of the morphism, but it will also follow the structure of the original work where the morphism is applied. That's it.
Okay. So if there are no other questions, I think we can thank you again.